Greetings, everyone. I hope you can see me in the bottom right corner as I wave an introductory hello to all you in Bedford. I'm a space and planetary scientist. My students called me Dr. D, but you can call me Camille's grandma. I received a list of very good questions about astronomy from your class, so I'm going to take a few minutes of your class time to give my version of the best answers I can. Now, that might sound a little bit fishy, spacey, kind of like this person in space, seemingly free from gravity, but actually not. Well, that's because in the field of science, answers about how things came to be or where the energy or galaxy organization originated are only the best answers we can give right now with our human reasoning, which can be flawed. So from the outset of this lesson, I want you to know that God's wisdom far outweighs our own. Even our best minds are unable to understand how, when, or where the universe came to be, but God certainly knows. Modern science pulls back from any mention of supernatural intervention, so from modern science, it's impossible to get the rest of the story. Now, with all that said, I do love science and the discoveries we can make using our own wits and our five senses. So let's take a look at your class questions, beginning with question number 1. What do you think is the most exciting unanswered question in astronomy right now? Well, in my estimation, I would say, why do very distant galaxies appear fully formed and evolved? That goes against what science currently has theorized. So why is that important? Well, scientists believe the further in distance we look back or look away, the younger the galaxy should appear. What might be known as an irregular galaxy should be the norm. But we haven't found this to be true with our newest James Webb Telescope images. This could be for many reasons, but keep in mind modern science theories don't accept fully formed objects or beings like ourselves as coming first. So they need baby people or baby galaxies first. As Christians, we accept God's creation of Adam and Eve fully grown, not coming from earlier ancestors of apes. 2 Timothy tells us people will reject sound doctrine, turn from the truth to fables, and have itching ears that prefer to listen to the things they want to believe, which we might call being willingly ignorant. What did you do as an astronomer? Well, I taught astronomy at our local community college. I interpreted the geology of Titan, and that would be the surface of Titan, Saturn's moon. And then I used what I learned to predict the future of the surface of Titan's moon. So those are just some of the things that you would do as a scientist or as someone that's an astronomer. And what made me want to be an astronomer? Well, I think seeing the images and seeing the skies in software programs where you could actually look back in time and know exactly the position of the stars and planets, and that they were so precise, it was fascinating to me. Needed no battery replacements, yet they kept perfect time. Genesis 1:14 says, "Let there be lights in the expansion of the sky, so it separates the day from the night. They will serve as signs for seasons and for days." Who is your favorite, most interesting astronomer? Next question. Tough question, that one. I'll choose for most interesting Tycho Brahe. He recognized that both Ptolemy and Copernicus models were observationally and mathematically off. Ptolemy was the Earth-centered and Copernicus the Sun-centered model. He realized that in order to choose the right answer, it required better data. He knew that garbage in equaled garbage out. Now, at age 2, Tycho was sent to live with his aunt and uncle. None of his siblings were ever sent there, but he was. And then at age 20, He lost his nose in a duel with his cousin over who was the better mathematician. It was probably an unwise thing to do, especially at night, but he became very widely recognized because of his gold or his silver or his brass noses. He also had the very best, largest, biggest equipment for measuring the position of things in the sky, such as stars and planets. Now, with that great equipment, Tycho was able to get some of the best positions of the stars and the planets, and also some of the best mathematicians to figure out how they were in these various positions at various times. Well, Tycho did not want Kepler to actually use the sun-centered or Copernican model. He really felt like Aristotle's insistence on perfect circles and perfect cycles, and also a Earth-centered solar system, were probably the correct way. But as you can see on the model down in the center, bottom center there, he wanted to have the sun with all the other planets orbiting it, and then the Earth with just the moon and all the other planets and sun orbiting it. It was quite complicated, and Kepler was able to show that it wasn't right. Even though Tycho would be the most interesting of the astronomers, and he got some things right, he was definitely wrong about the Earth-centered model. But he did turn over some great measurements and positions that Kepler was able to devise and come up with the 3 laws of planetary motion that were revolutionary. They followed the Copernican model, and when it comes to astronomers whose ideas affected astronomy the most, Copernicus be the number 1 there, number 2 being Kepler, who actually put the mathematical and scientific laws to it. Henrietta Leavitt, she was an amazing astronomer, coming up with the period luminosity for variable stars, and Hubble with the distances that he was able to determine actually from Henrietta Leavitt's pulsating or Cepheid variable stars. Now, they aren't the ones I chose as the number 1 though. Aristarchus of Samos, 1800 years before Copernicus or each one of these astronomers, had already devised a very good model of a sun-centered solar system. His ideas were taken up by Copernicus 1800 years later, but he really was the first and the brightest. The problem that he faced was Aristotle's shadow. He lived not long after Aristotle, and nearly everyone had jumped on Aristotle's bandwagon for almost all science and philosophy ideas, and that lasted and caused problems for about 1500 to 2000 more years. Have you ever seen the gap in Saturn's rings? That's my next question. The answer is yes. I've seen the Cassini division in my own telescope. As for other gaps, I've seen them in larger telescopes. The Cassini division you can see in this image is caused primarily by Mimas, which some people say is a very good look-alike to the Star Wars Death Star. Well, another fun question is, did I ever want to go to space? And did I? Well, absolutely yes. I would have loved to have gone to space, but no, I wasn't able to. However, I would settle for a jet suit flight if I ever get the chance. How about you? Well, here's wishing you all smooth sailing through one of the oldest sciences of the ages, even older than Camille's grandma, through the oldest jokes in the universe, pretty much, and through Kepler's laws. That is after the next slide if you want to tackle a little bit of math. So for the oldest jokes, well, if you could put Saturn into a bathtub, it would float. But watch out for the rings it leaves behind. So here's where the suffering comes. Number 1, where does an astronomer park his spaceship? At a parking meter, of course. What happened to the astronaut who stepped in bubblegum? Got stuck in orbit, of course. And why did the star get arrested? It was a shooting star, of course. And it was an imposter for a star because all shooting stars are actually meteors. The end. So there was another question. Can you explain Kepler's laws? Well, the first thing that you probably want to know about Kepler's laws of planetary motion was how it ended up working for him. Well, the number one creative leap that he was able to make was that the movement of the planets around the sun was not in perfect circles or epicycles as Ptolemy and even Copernicus and Brahe, what they felt like needed to be the case. It was simply that they were slightly oval, slightly elongated. Just keep in mind that it's slightly. The images that you see in the middle there of an ellipse are way out of proportion with the actual situation that we have with the planets and their motion around the sun is not that eccentric or that oval. Now, just as models of our solar system tend to be off in their amount of eccentricity, so do models of our planets. This is a pretty good model, actually, where you're seeing the difference in the size of Earth as opposed to the other planets. But I will say that we rarely get to see a model like this when you see images or other pictures portrayed of our solar system. So keep that in mind with all the images I'm getting ready to show you on Kepler's laws. Number one law being simply that it is an ellipse, although not nearly as eccentric or oval as the image that we have right here. Kepler's second law, that as a planet moves around in its orbit, it sweeps out equal area in equal times. So you can see the image here where you have the blue area, and at perihelion, the planet is moving much faster and covers a larger part of the arc, whereas at aphelion, when it's furthest away from the sun, it covers a shorter distance in the same amount of time. But because it's farther away, the area ends up being equal on both sides or anywhere throughout the measure of a time period, like a month, as it travels around its elliptical orbit. But what you can actually know from the understanding of this law is such laws of physics as the conservation of angular momentum and energy, or the laws of gravity. These are also part of the reason why it works this way, that our planets will sweep out equal area in equal time, whether it's the Earth or any other planet in our solar system. Okay, final slide and Kepler's third law. More distant planets orbit the sun at slower average speeds, obeying the relationship p squared equals a cubed. Now, why does this work? Well, for one thing, we are comparing the distances. The further distance a planet is, in every situation, it slows down. So we have Neptune out the very furthest planet, and it's the slowest of all the planets. And guess what? Mercury, the closest planet to the sun, is the fastest. In fact, that's why he's named after the Greek god of speed, Mercury. All right, but we need to understand how you find P. Well, P, the orbital period of Earth in years, well, that's just going to be 1. So it takes the Earth 1 year to completely orbit the sun. So Earth's P would be 1. Now we compare all the other planets' periods to the Earth's, so that if we want to figure how long it takes Saturn, we say, well, Saturn took 30 Earth years to complete an orbit. So we are comparing it already to Earth years. That means 1 would represent Earth for P, and 30 would represent Saturn for P. Now, when we get to A, we're talking about the average distance from Sun to Earth, which just represents half, or the semi-major axis of that ellipse that we were talking about. So the semi-major axis, it's like a radius, but it's slightly elongated. So we just take that, half it, and that becomes our astronomical unit, equal to 150 million kilometers or 96 billion miles. All right, now every other planet is compared to Earth's distance or astronomical unit. So we have Jupiter about 5, sometimes close to 6, but AU distances. We have Saturn at close to 10, 9.75. And in this case, if we were to use Saturn in this equation, P would be 30, because it takes 30 Earth years, that's its period. So it'd be 30 squared is equal to, and then the A would equal 9.75 cubed. And if you calculate that out, if you use the real actual numbers, not the rounded off numbers, you would find that they would both be equal to right at 900. So 30 squared is 900, and 9.75 cubed is about 900. All right, and with Earth, you plug in a 1. 1 squared is 1. A cubed, which would be 1 cubed, is 1. So it also equals with Earth. But everything can be compared and calculated that way. So if people were able to observe the period of a planet as it orbits all the way around the sun, then they could figure how far away it was using this particular you would say geometry, but you would say algebraic equation. Thank you all very much. I hope you understand it maybe just a little bit better, but I love the chalkboard, so I'm sure your teacher can do a chalkboard presentation on it too. Thanks. Bye.